Okay, it's Brian, and we're back here for round 2 of talking about nuclear physics. I'm going to start with a installment of things I like about your generation. And here's something that I'm seeing. Everybody's trapped at home and everybody is kind of like doing things in different ways than you would like to. But you are a group of people who has stayed positive about this. You are a group of people who really blooms where you're planted, and I really have that sense about you, and I really, really appreciate it. So you're putting up with this difficult time with remarkable alacrity, and it's much appreciated. Now I want to talk about half-life, and we talked about this previously. We talked about the fact that if you have a radioactive nucleus or a collection of radioactive nuclei, you're going to have this decay, and it's an exponential decay, and so every half-life, the number of atoms you have is going to decrease by half. Remember that concept. We also saw that the activity decreases with the same relationship because the activity R is just proportional to the number of atoms that you have. Activity is the rate of decay, and since a certain number of atoms, or a certain fraction of the atoms decay in every interval of time, as the number of atoms goes down, so does the activity. The unit that we use for decay is the becquerel. That's the SI system of units, and a becquerel is 1 decay per second. But sometimes there's an older unit that people use, which is the curie, and you'll see this from time to time. And 1 curie is 3.7 times 10 to the 10th becquerels. So typically, if we're having activities for typical sources, becquerels is going to be in megabecquerels. For curies, it's going to be in microcuries. We're kind of a typical thing, because the curie is big and a becquerel is small. Now here's something that I want to stress. Short half-life means a high activity. Because if I have a short half-life, it means the atoms are very likely to decay in the next interval of time, and so as a consequence, there's going to be a lot of atoms which are decaying. Short half-life, high activity, and the activity or the decay rate is equal to 0.693 times the number of atoms divided by the half-life. And so you can see if I have a short half-life, I'm going to have a big activity. Here's a chunk of plutonium-238, which they actually use to power spacecraft, not by the radioactivity, but by the heat. This chunk of plutonium-238 has a half-life of 88 years. That's short enough that it actually is hot. It is literally hot because from the energy released in the radioactive decays. And you can use that heat to drive a heat engine to run a spacecraft. Now, I want you to take a look at this key concept video I made about uranium and radium, and it turns out uranium has a much longer half-life than radium. They occur together in the same ores, but the radium has a significantly shorter half-life, and so therefore a significantly greater activity. So take a moment and take a look at that video. One of the things that kind of came out in that video was people had this idea that radiation was something that was healthy. It was something that was good for you. And back in the day, there were all these radium cures that were postulated. People would say, like, oh, if you're feeling run down, we just need to get more radioactivity in you. This is a really, really bad idea. And if you got radium cures, you were lucky if you got them from a quack who didn't actually use radium, because radium was expensive. Now, it turns out there's still some belief in this which persists. And you can go up to Montana and hang out in the free enterprise radon health mine, and there's this theory that a small amount exposure to a small amount of radiation will like stimulate your immune system or something like that. Probably nothing to it. But on the other hand, hanging out with a bunch of like-minded folks in kind of a cavern might be kind of a pleasant way to while away an afternoon. It's probably not going to damage you, but because the amounts of radiation people are exposed to are relatively small. But I don't think that's a good idea. Now, if the activity is really short, and for instance, the radon progeny, radon has a half-life of like 4 days, but it decays into stuff which has half-lives measured in minutes. And so the short-lived radon progeny can have very, very big count rates, very, very high activities. And that's how, in that one video that you saw, I was able to get a decent count rate off a balloon by rubbing it on my hair, and it collected dust from the air, and some of the dust will contain particles of these radon progeny, and a very small number of atoms can nonetheless give a big count rate because the half-life is so short. Now I want you to think about the decay chain that we have here. Uranium-238 is found in the Earth's crust, and it has a half-life of 4.5 billion years. It's an alpha emitter. It decays with the emission of an alpha particle. And this glass here, this is uranium glass. We had a chance to see that in the video as well. The uranium glass was made by putting uranium in the glass, and it gives this awesome green color and also makes it fluorescent. When this uranium glass was first made, it didn't register on the Geiger counter, and now it measures hundreds of counts per minute. What would be the difference? What would explain the change? I want you to think about that. I'll be back. Well, there's two factors that are at work, and one factor that's at work is this. Uranium's an alpha emitter. Okay, when you emit alpha particles aren't very penetrating. The alpha particles won't make it out of the glass. But it decays into thorium-234, which has a very short half-life, and that emits beta and gamma particles. They will make it out of the glass. They will make it out of the glass. The other thing that happens is it works its way down the decay chain. Uranium-238 is not that radioactive because the half-life is so long. But the stuff that it decays into has significantly shorter half-lives. And so since you have significantly shorter half-lives, what that means is you're going to have significantly higher activities. So the radioactive species that are produced have decays that are more penetrating. They make it out of the glass, but also the decay rates would be much higher. Those are the two pieces of the puzzle. Now I want you to think about this. 2 billion years ago, well, actually there's two main isotopes of uranium, uranium-235 and uranium-238. 2 billion years ago, uranium-235 was about 3% of the uranium in the Earth's crust, okay? Now that's dropped to 0.7%. So my question is this: which of the two isotopes has a longer half-life? Then the second question is, if I have equal size masses of uranium-235 and uranium-238, which sample will have a higher activity? I want you to think about that. I'll be back. Well, of course, if we had 3% of the uranium was uranium-235, and now it's 0.7%. What that says is the uranium-235 is going away faster than the uranium-238. And so uranium-238 must have a longer half-life. Since that's true, if I have two samples of uranium-235 and uranium-238 with exactly the same mass, that means that the uranium-235 with a shorter half-life is going to have a higher activity. You know that that has to be true. This picture that's in the background is actually a picture of a natural nuclear reactor that was found in the Earth's crust. And it turns out when uranium-235 was 3% of the uranium, uranium-235 is fissionable. That's the stuff they use in nuclear reactors and nuclear weapons. And so it turned out there was enough uranium-235 in a pure enough ore that you could have a naturally occurring nuclear reactor in the rock. It was kind of an awesome thing. And as we saw, longer half-life, uranium-238. And that means if I have two equal mass samples, the uranium-235 is more active. Let's do a quick calculation, and there's a point to this one. I want to know, what is the activity in becquerels and curies of 1 gram of radium-226? Okay, and then once we've done that calculation, we're going to come back and look at the second sentence. Marie Curie was the discoverer of radium. Can you see where the unit of activity named after her came from? Oh yeah, and I think you'll be able to see this. So we have 1 gram of radium-226. Well, remember, the activity, okay, the activity is proportional to the number of atoms. And so a first step would just be to compute the number of atoms. So start with that. How are you going to make that happen? And then where are you going to take it? Go ahead and start calculating. I'll be back. Well, the equation that we're going to use to guide our process is this one right here. Okay? The activity is equal to 0.693 times the number of atoms divided by the half-life. So we just have to get the number of atoms, and we can start with this. What is the mass of 1 atom of radium-226? Think about that for a second. We're going to use the quick and dirty version. And the quick and dirty version is the mass is going to be 226 atomic mass units. And then the question asks how many atoms are present in the sample. Well, I've got 1 gram, so that's 0.001 kilograms. That's the number of atoms in the sample. If I divide that by the mass of an individual atom, that will give me the number of atoms. If I know that, and I know the half-life, I can compute the activity in becquerels, but becquerels is decays per second. And since becquerels is decays per second, I have to take this 1602 years, and I have to convert that into seconds, okay? So then I can go ahead and compute the activity in becquerels. Having gotten it in becquerels, I can convert it to curies. So keep calculating. I'll be back. And what you find is this. The quick and dirty form of the mass, 3.75 times 10 to the minus 25th kilograms, given that it's a 0.001 kilogram sample, I have that much mass per atom, I have this many atoms. The half-life of radon, and I put it in seconds, is this. And so then I can use my basic relationship to calculate the activity. In becquerels, is 3.7 times 10 to the 10th, or in curies, 1.0 curies. And that makes sense because Marie Curie was the discoverer of radium. And the key fact about radium is it's radioactive. That's why it's called radium. And the activity of 1 gram of radium is 1 curie, which makes a lot of sense. Now, I want to remind you of the most famous equation in the world, E is equal to mc squared. And what it says is you can freely convert energy to mass, or you can freely convert mass to energy. And in nuclear reactions, you're going to see that occasionally the mass of the products are going to be less than the mass of the reactants. And when you lose mass, that just means you've lost energy. In principle, that's a thing in chemical reactions, but the energy is so small that the difference in mass is not noticeable. Because the amount of mass that corresponds to energy, it's a lot of energy for a small amount of mass because you multiply it by c squared. And c is the speed of light, which is 3 times 10 to the 8th meters per second. So you're multiplying it by 9 times 10 to the 16th. So a small amount of mass lost corresponds to a huge amount of energy. Now, if we take 1 atomic mass unit of mass and we convert it directly to energy, 1 atomic mass unit gives us 931.49 mega electron volts. That's a value that we'll use frequently in the calculations to come. Now, it turns out you can turn mass into energy, but you can also turn energy into mass. In this picture, I see I've got a photon that comes in. Photon comes in, and then it stops, it hits something, and the energy of the photon is lost, but you can't lose energy. And what it produces is a positron and an electron. And the positron and electron both go in these circular paths. And the reason is because there's a magnetic field that's making them go in orbits, basically. And as they lose energy, the size of the orbit gets smaller and smaller and smaller. And so you've made an electron and a positron out of nothing. And a positron is an anti-electron. It's exactly the same as an electron, but opposite. It's got a positive charge where an electron has negative. And an electron, an E minus, plus an E plus, when you add them together, what you get is just energy. You can produce them from energy. And if the matter and the antimatter come together, they completely annihilate, and then they produce just energy. But the interesting thing is, if I have a gamma ray of sufficient energy, it can just produce one. Out of the void, it produces this electron-positron pair. Here's a question. What is the minimum energy in MeV of a gamma ray if it was going to give rise to an electron-positron pair? I want you to do that calculation. I'll be back. Well, the way we'll solve this is we're going to use the most famous equation in the world. E is equal to mc squared, okay? And the mass that we have here is going to be 2 times the mass of the electron. And I'm looking for the energy necessary to make that, because it's 2 times the mass of an electron, because a positron has the same mass as an electron. I can do it that way. The other thing I can note is that 1 atomic mass unit corresponds to an energy of 931.5 mega electron volts. So if I can take the mass, twice the mass of an electron, convert it into atomic mass units, I can just scale the appropriate amount of energy. So go ahead and complete that calculation. And what you get is this, okay? The mass, 2 times the mass of an electron, 18.2 times 10 to the negative 31st kilograms. E is equal to mc squared. I get this many joules, and I convert that into mega electron volts. It's 1 mega electron volt. That's the minimum energy photon necessary to produce an electron positron. Now, over the course of a day, the sun gives off lots of energy, and because the sun is losing energy, it must also be losing mass, because mass and energy are related by this relationship. E is equal to mc squared. And if I figure out how much energy the sun loses every day, I can work out how much mass it loses. And the answer is 350 billion tons of mass. And that's mass being converted into energy every day. Crazy. Now I want to look at this concept of binding energy. Okay, a helium is made up of 2 neutrons and 2 protons plus 2 electrons. If I separate into components, that's basically 2 hydrogen atoms plus neutrons. So these are the raw materials that I would use to build a helium atom. But if I look at the masses, the mass of a helium atom, 4.00260 atomic mass units, that is less than the mass of 2 hydrogen atoms plus 2 neutrons. So I go from this amount of mass to that amount. So that means if I took 2 hydrogen atoms and 2 neutrons and I built a helium atom out of it, energy would be released in the process. And in fact, that is the basic process that happens inside the sun that leads to the sun's production of energy. It's this process right here. I take these hydrogens and I turn them into heliums. And as I do that, mass is lost. And as mass is lost, energy is formed, and so that energy streams out through space, and that's what powers the Earth and all life on it. Now, I want to do a quick calculation of the binding energy for different atoms, but I want to note we can compute how much binding energy there is, because it has, this is my difference in mass, it's this, and I can convert that into mega electron volts. That's the amount of energy that is created when I form a helium, or it's the amount of energy that would be required if I wanted to bust up a nucleus of helium. That's how much it would require me. But typically, the way I write these numbers is not in the binding energy, just total. I do the binding energy per nucleon. So per nucleon in helium, it's 7.075 mega electron volts. That's the binding energy per nucleon. So it's the number for binding energy divided by the number of nucleons, which is 4 in this case. Okay, let's take a look at another atom. Now I want to look at this concept of binding energy. And I want to look at iron 56, and there's a reason for doing iron 56 in particular, and I want to know the binding energy per nucleus. Now the mass of iron 56 is this, the mass of a hydrogen is this, the mass of a neutron is this, and 1 atomic mass unit is equivalent to this energy. So the question is, what is the binding energy per nucleon of iron 56? I want you to think about how you would solve this problem. Go ahead and get started. I'll be back. Now, of course, the way we're going to start is this, okay? The mass of an iron 56 is this. But iron 56, its atomic number 26. If I wanted to build an iron 56, it would take me 26 hydrogen atoms plus 30 neutrons. So if I take the mass of 26 hydrogens plus the mass of 30 neutrons, that's the mass of the stuff that makes up the iron 56. And then I look at the mass deficit. I add that up That's what I start with. I finish with 55.934940. Oh, by the way, notice the big number of decimal places. We have to do that because we're taking differences between numbers that are extremely close to each other. What difference in mass do I get? And then I'm going to convert that to mega electron volts as using that relationship right there. So keep calculating. I'll be back. And what you get is this. I get 26 hydrogens plus 30 neutrons minus the mass of the iron 56. The difference in mass, the mass lost when I build an iron 56 from raw materials, is 0.52846 atomic mass units. And converting that into mega electron volts, 492 mega electron volts, that's 8.79 mega electron volts per nucleon, and that is the biggest number of any nucleus, and so iron 56 is the most stable nucleus that there is, and that is an important part of a story that we'll tell shortly. Now let's look at fission. You get energy out of really heavy atoms when you split them into smaller fragments, okay? And we want to do this. We want to do a calculation for a nucleus of plutonium-240. You can, and it fissions, it makes smaller fragments. One of the possible fragments is xenon-133. I want you to work out the binding energies per nucleon of the plutonium-240, and the possible fission product is xenon-133. So I want you to see what you get for those. Do the calculation just like we did the one for iron. Go ahead and dig in. I'll be back. And of course, to make a plutonium-240, that's going to be 94 hydrogens plus, let's see, 146 neutrons. Making up a xenon-133 is going to take me 54 protons plus 79 neutrons. Oh, no, not protons. It's going to take me 54 hydrogen atoms plus 79 neutrons. And so I'm going to add the mass of, find the mass of the products that I have for each of these cases. And I'm given the mass of the reactants. And then I have the mass of the products. I'm going to figure out how much mass is lost, convert that to energy just as we did previously. When we do that, what we find is for plutonium, it's not very much. For plutonium, I get 7.55 mega electron volts per nucleon. For xenon-133, I get 8.41 mega electron volts per nucleon. So there is more binding energy for the xenon than for the plutonium. So if I could take plutonium and split it into xenon plus other atoms, energy is released in the process, and that is where the energy comes from in fission explosions, or also in nuclear reactors. It's from fissioning from heavy, less stable nuclei into lighter, more stable nuclei. But another way you can get energy is you can get energy by fusion. If I take lightweight atoms, I can put them together and I can get energy out. And I want you to do a quick calculation. So helium-3 has a binding energy of 2.5 mega electron volts per nucleon. Lithium-6 has a binding energy of 5 mega electron volts per nucleon. So here's my question. Would it be energetically possible for two helium-3s to fuse together to make a lithium-6? And if so, how much energy would be released in the reaction? And don't worry about the exact details, but in fact, this is something that you could do. Another particle flies off, but basically, if you squeeze together two helium-3s, you could make a lithium-6, but is it energetically possible? Go ahead and think about this. Think about how you're going to set this up, how you're going to do it. I'll be back. Well, let's start by taking a look at about how this works. So I start out with two helium-3s, and I'm turning that into one lithium 6. Now let's think about the binding energy per nucleon. Over here, I've got 3 nucleons in each of my helium-3s, and so I have a total of 6 nucleons because there's 2 helium-3s. The energy is 2.5 MeV per nucleon. So the energy, the binding energy, total, is 6 times 2.5 MeV, and then over here, I have 6 nucleons, but the binding energy is 5 MeV per nucleon. So it's 6 times 5 MeV. So I go from this number, which is 15 MeV, over to here, which is 30 MeV. So as a consequence, I go from 15 MeV to 30. That's my binding energy. I've ended up with something which is more tightly bound than what I started with. And since I've gone to a situation that's more tightly bound, I release a different amount of energy. As a matter of fact, if you did this fusion, you would release 15 million electron volts of energy. And fusion reactions are extremely energetically, they produce a great deal of energy. And you can see that from this calculation. Now, if we look at the curve of binding energy for nucleons, it looks like this, okay? The lightweight atoms have low binding energy. The heavyweight atoms have low binding energy. The maximum is right here at iron 56. If I have lightweight atoms and I combine them into heavier atoms, I get energy out. If I have heavy atoms and I bust them up into smaller atoms, I get energy out. I can get energy by fusing the lightweight atoms or by fissioning the heavyweight atoms. And that's how you get energy, by fusion or fission in nuclear reactions. But here's the question. Where did the heavy elements come from? If it's energetically favorable to take uranium, as in this uranium ore, and break it into smaller fragments, what's it doing in the first place? How would you make a heavy element? Because it's energetically unfavorable. The only way you can do it is to have some sort of a situation that is incredibly energetic. And it turns out that's what happens. In supernova explosions, there is so much energy released that atoms will actually fuse in a way that absorbs energy. They're basically endothermic reactions that are happening inside here, and they don't happen spontaneously. They have to be forced together at high speeds, high pressures, high temperatures in order to make those. And so you need to have a supernova explosion to make those heavy elements. So if you think about this, like the helium in the helium balloon that I gave someone at the beginning of the previous class, think about this. It began with a supernova explosion. So it began with a supernova explosion 6 billion years ago. And the debris from that supernova explosion formed the disk that coalesced to form the Earth and the planets. And some of the uranium-238 in that material from the supernova explosion formed rocks in the Earth that get buried deep below the surface. The uranium atoms decayed over time. Each decayed uranium atom made an alpha particle. Those alpha particles are helium gas, which was collected deep underneath the surface of the Earth. Someone drilled for it, collected the helium, put it in tanks, delivered it to a store, put it in a tank. I put it in a balloon, and I gave it to you. That was a process that began 6 billion years ago. And so when I gave that balloon to somebody, I said it was very, very special. That was a gift 6 billion years in the making. And I want you to think about that next time you see a helium balloon. Now I want to talk about radiation exposure, because radiation that we're talking about this week is ionizing radiation. The alpha particles, the betas, the gammas, they will ionize matter. They will damage nuclei of atoms. They will damage nuclei of cells, the other kind of nucleus that you guys are familiar with. And so we want to worry about radiation exposure and trying to quantify it. And we do it using the gray and the sievert, okay? 1 gray is 1 joule per kilogram of absorbed energy. And basically, ionizing particles deposit energy in other materials. So a beta particle comes in, it's depositing energy as it goes. 1 joule per kilogram of absorbed energy is 1 gray. And then I multiply it by the relative biological effectiveness, which is a measure of how damaging different kinds of radiation are. So take the dose in grays times the relative biological effectiveness, and I get a dose equivalent in sieverts. And typically for the types of things that we're going to be looking at, the relative biological effectiveness is 1, because we're going to look at X-rays, gamma rays, and betas. That's mostly what we'll consider. And how much is a big dose? 3 millisieverts is a typical yearly dose. So if we take the amount that is deposited in your body by ionizing radiation in the environment, it's 3 millisieverts. That's a typical yearly dose. And that's reasonable. You can be exposed to that. It doesn't seem to cause huge ill effects. 350 millisieverts at one go will cause symptoms of radiation poisoning. 5 sieverts will kill you. That's kind of the lethal dose of radiation. So those are numbers that you can help put those things in perspective. Now I want to do some radiation dose calculations, and there's 2 different kinds of doses we're going to consider. External, that's radiation from the outside, or internal, where it's inhaled or ingested. And it turns out we can calculate numbers for both of those kinds of exposures, but to put it in perspective, the natural background radiation is 3 millisieverts per year, okay? That's what we're going to compare it to. And that's the amount of radiation that we're exposed to on a yearly basis. And so if you're talking about getting a dental x-ray, that's 1% of the natural background. Well, you want to think twice about it. That's basically 4 days worth of radiation. So it's probably not hugely worrying. A transatlantic airplane flight, interestingly, is a reasonable amount of dose. We'll talk about that later. Chest x-ray is a tenth. That's a month's worth of radiation dose. A PET scan, 7 millisieverts. That's 2 years worth of dose. And so you want to think twice about those nuclear medicine procedures because the doses are significant. And whenever I have radiation, I always ask, whenever I have an x-ray or a CAT scan or whatever, I say, what dose am I getting? Give it to me in millisieverts. I just want to know. I want to know. And typically, the risks of not having the test or having the treatment outweigh the risks of the radiation. But you just want to know. You want to be aware. Now, I want to note, different animals are more or less susceptible to radiation. For you, a 5 sievert dose is lethal. For a tardigrade, they can survive 5,000 plus sieverts. They're incredibly hardy. As I'm sure you know, they're awesome little creatures. Super, super hardy. They can withstand drought. They can withstand radiation. They can withstand high temperatures, low temperatures, etc. Crazy, crazy little creatures. Now let's talk about internal doses. And it turns out over the course of a year, you probably get about 0.4 millisieverts dose from food you eat. And typically, it's in the form of potassium because one of the isotopes of potassium is potassium-40. And lots of foods have potassium in them, for instance, peanut butter and bananas. So if you ate 1,000 bananas, you would get a significant dose of radiation. Same if you ate 40 tablespoons of peanut butter. But here's the thing. Go ahead and eat bananas, go ahead and eat peanut butter because there's potassium in every cell in your body. And eating a lot of peanut butter is not going to increase the amount of potassium measurably. So eat peanut butter, eat bananas, it's fine. You're going to get a potassium dose from it, but you're getting a potassium dose from it anyway. On the other hand, here's a place where you're going to get a significant dose. Smoking. If you're inhaling particles into your lungs and you're going to have 30 millisieverts dose. That's 10 times the natural background dose to your whole body, and it's mostly to certain tissues in your lungs. So this is bad news, and that's part of the reason why smoking is dangerous. I mean, you didn't think this was a healthy activity, but this is one of the reasons why. You inhale radioactive isotopes, and they damage sensitive tissues in your lungs. So go ahead and eat some peanut butter on a banana, and it's fine, but if you're a smoker, I want you to think twice about that. Now let's do a quick dose calculation. Suppose a 60 kilogram laboratory worker receives a whole body X-ray exposure corresponding to this many photons of this wavelength. What is the dose equivalent? And that is an exposure. There was a particular accident that was looking at, and this person got that dose. And so that's the kind of thing that you could imagine happening. Here's a situation where it could happen. Here's an early engraving of someone getting an X-ray, and you can see here's the X-ray tube producing X-rays that are coming out. They're going through him. Here's the doctor looking at the X-rays on this phosphorescent screen. Both the patient and the doctor are getting ridiculous amounts of X-ray exposure. People were really, really cavalier about that stuff back in the day. But let's go ahead and do this calculation. And let's think about how we start. Okay, so 1 gray is 1 joule per kilogram. Okay, and we're going to start by computing a dose in grays. Well, I have this many photons of this wavelength. Oh, if I have the wavelength of the photons, I can calculate the energy of the photon. And I know how many photons I have, and so I can calculate the total energy of the dose. And if I can calculate that, I can take the energy of the dose, and I'm going to divide it by the mass of the laboratory worker. That'll give me the dose in grays, and I can do the dose equivalent in sieverts, but since the RBE is 1, the dose in grays is just equal to the dose equivalent in sieverts. So go ahead and do the calculation. I'll be back. So the photon energy, and I did it using our 1240 calculation and then converting, I get this many joules per photon. So the energy that's absorbed is that many joules per photon times the number of photons. It's this many joules. The dose is the absorbed energy divided by the mass, which is 0.5 milligrays, and then that turns into 0.5 millisieverts. And so that will be comparable to a chest X-ray. And my assessment is Brian wouldn't give us a problem where I was significantly damaging somebody. I mean, that's something that was noticeable, something that's worrying, but not something that is going to be immediately dangerous to the person. Here's a question for you. What occupation in the U.S. has the highest yearly radiation exposure? Is it these people in coronavirus protection suits? Oh, no, I'm just joking. These are actually nuclear workers. You can see someone's holding a Geiger counter here. What is the U.S. occupation with the highest yearly radiation exposure? I want you to think about that for a minute. Don't Google it. Just cogitate. Turns out it's flight attendants. And you're saying like, what? Flight attendants? Is that because of like nuclear powered airplanes? No, it's flight attendants because a significant fraction of the radiation that you're exposed to comes from above in the form of cosmic rays. And when you get higher up in the altitude, you're just closer and closer to the cosmos, closer and closer to space, which is where the cosmic rays come from. And so here's a graph I made when I took a Geiger counter on an airplane going across the Atlantic, and they had a little readout that told me how high the plane was. And I could just measure how many counts per minute as a function of height. And as the plane got higher and higher and higher, the count rate went higher and higher and higher. On the tarmac, I was getting about 10 counts per minute. Up at elevation, I was getting 350 counts per minute. And so significantly higher radiation dose, and it's mostly in the form of these cosmic rays. And flight attendants spend a lot of time up at those high elevations, so a consequence, they get a pretty significant radiation dose. And they get about 5 microsieverts per hour from cosmic rays. So how many hours of flying would it take in 1 year for a person to double his or her yearly radiation dose? I want you to do a quick calculation and see what you get for that. And what I see folks getting is 600 hours. And by the way, I just see that in my mind. I am imagining you out there doing those calculations. 600 hours of flying doubles your yearly radiation dose. So flight attendants get 80 hours a month typically, or 960 flight hours a year. And so what that means is that's more than doubling your radiation dose. It's probably okay because if you live at higher elevations, you get more, and people who live at higher elevations seem to be doing okay. But it's just worth noting. Now, next time, I'm going to talk about forms of radiation that aren't natural, i.e. that's produced by nuclear weapons, nuclear explosions. We're going to tell the story of Bert the Turtle. This is Duck and Cover, Tales of the Atomic Age. I'll see you then.